So this week, we're delighted to welcome Mahoney. Michael's a professor of statistics at Berkeley, so the vice president and director of the Big Data Group, the International Computer Science Institute, and he's the group lead for machine learning analytics at Lawrence Berkeley National Lab. Today, he'll be speaking on random matrix theory and modern machine learning. Let's welcome Michael.
Well, thanks, everyone. Thanks for the invitation, and it's good to be here. I was only able to be here for today, so it's a quick in and out, but I've been here before, and I'm sure I'll be back again, so it's great to be here, though, even if it's quickly. So I guess what I want to tell you about is some work we've been doing that's we're trying to combine a couple threads, and random matrix theory is this very technically complicated topic. I mean, I assume everyone's here for this and the machine learning sort of incidental. But machine learning sort of provides a forcing function that I think complements traditional random matrix theory. So I want to describe a little bit of that. This is actually, I think there was a 2 or maybe 3 hour, 4 hour version of this I gave last June. This is sort of a condensed version of that. And even right now, there's a few too many slides. So if you want more details, that's available online. This will be available online. And if you want fewer details, just sit back and squint and I'll sort of describe some of the key ideas. Because there's a few key ideas that I think are sort of interesting, maybe. All right. So random matrix theory, it's one of these things that's extremely broadly applicable, but because it's so broad, you've got to fine tune it to different applications in certain ways. And I think the 99% use case boils down to computing eigenvectors. It makes typically asymptotic statements or physics-style statements, a little different than non-asymptotic you see in machine learning. And so I think machine learning, there's two things here. One, you can use random matrix theory for certain problems in machine learning. I'll give you a hint of some of those. And maybe some of the less obvious ones that I think stress tests sort of the methods a little bit more. But also, the fact that machine learning is asking different questions than you typically ask is sort of a forcing functions to expand sort of the convex hull of what random matrix theory is and what it can do. So it actually goes sort of in both directions. All right, so I'll talk a little bit. I think there's 3 slides each on these first 2 things. So one is, a lot of people are doing these things these days in machine learning, which de facto means neural networks. It could be kernels and other things, but it's presented as neural networks, even if the theory it's infinitely wide, so it's really a kernel. But the motivation is neural networks or algorithms. And what you typically people want to do is work with eigenvectors, and if you see what is a separation between a bulk and a spike, signal and noise, you do something and declare success. And that plays well with what random matrix theory has done historically, which is look for like a Marchenko-Pasteur type distribution, look for signal spikes. Question. If I'm going to apply random matrix theory to modern neural networks, what do they look like? Do they actually have this structure, or do they have a structure that's like completely different? And that's an empirical question. So you can go and ask that empirical question, and the answer is they look completely different. So I'll describe in 3 slides how they look different. We could talk for hours about that. It's an interesting topic, but look at weight matrices. Unless Google's going to share all their data with me and all their compute, I'm not going to ask questions that depend on their data compute. I'm going to try and ask falsifiable questions. And so it'll be about the weight matrices, but the structure of the theory that will develop could be more broadly applicable. And then I'll talk about some on randomized linear algebra. This is something that is an area that we started about 10 or maybe 15 years ago, where we use randomness inside core linear algebra problems. And people have basically gotten a sketch, and that corresponds to a Johnson-Lindenstrass type thing, if you're familiar with that. And that's good, but it's a bit fat. It's a bit overkill. And so can you do better? And the answer is you can, but you need to use techniques that start to smell a lot like random matrix theory. So I'll describe those two. Those 2 are the motivations. And then I'll want to describe some theory. And the long story short on the theory is you can come up with sort of a weaker notion of convergence. So think of law of large numbers as a type of convergence where you get a very precise estimate on something. If you scale things in a different way, you might get a central limit type theorem convergence. You don't get sort of the exact point, but you get sort of an estimate, right? You flip their coins. Is the answer 1 million times? Is the answer 500,000? Or is it 500,000 plus or minus a few thousand? You get some distributional thing. And it turns out for a range of problems, you can get situations where things fail to converge even to that. But If you only ask certain types of queries, then they converge. And I'll be a little more precise about this, but linear queries or quadratic form queries. So linear queries give you something, traces and Stieltjes transforms, and a lot of traditional random matrix theory gives you eigenvalues. But in machine learning, you don't just want eigenvalues. You might want an eigenvector, right? Classification axis that you sweep along in a kernel method, or some variant of that in a neural network. So can you ask heavier duty queries, quadratic form queries or other queries, and come up with a deterministic equivalent, meaning a matrix that's not what you converge to, but that is deterministic. It could be randomized, but is equivalent to the thing you want if you ask a certain class of queries, quadratic form queries. And you might say, this is starting to sound exotic. I don't even want to think about this. But if you have a matrix A and you quantize it, because you're doing low precision, you come up with a matrix A prime. That's a nonlinear operation. If you feed it through a sigmoid nonlinearity, you're doing something nonlinear. So the question is, does everything go to hell and so you can do nothing? Or is there a sense in which in high dimensions you're approximately linear? And the answer is that you can formalize the latter. So this sounds a little bit exotic, but really you're just trying to do, quantify a sense in which you're approximately linear in a high dimensional sense. And then I'll talk about three applications, one, and they're all theory with implementations and so on. The first is a little more theoretical. I'll come up with a model, a random matrix style model that has the following properties. It has a scale on its entries. The entries are like the height of people. They're all 6 feet tall, plus or minus, a foot. But its eigenvalues, its correlational structure is heavy-tailed or power law, because that'll be the leading order thing we see in the WeightWatchers. So can you do that? And the answer is it's very hard to do, actually. I mean, typical random matrix models cannot do that. And so this will be an example of a model that can. So it can open the door to ask some of the first questions there. It also stress tests iterative algorithms and randomized linear algebra in interesting ways. The second and the third is, can you use ideas, basically slightly heavier duty from free probability theory, to make statements about eigenvalues in this case, but potentially more generally, for matrices that are so large you can't even represent them implicitly, which is a common model of access, but you can't even do matrix vector multiplies. And so think of this matrix that's 1,000 by 1,000 or 10,000 by 10,000. You put in RAM, you get something, and then the eigenvalues fall off at 10,000, of course, because that's the size of the matrix you work with. What if this thing was a trillion by trillion? It's possible the trillion by trillion thing is really 10,000 by 10,000. The eigenvalues go to zero. Right? Good luck. Can you make a statement about what the trillion by trillion thing would look like using only 10,000 by 10,000 or 1,000 by 1,000? And think of a neural tangent kernel. Right? People write this down. It barely exists in the sense you can't even represent it, or they write it down in pencil and paper. You couldn't store all the bits here, right? And so can you make a statement about the eigenvalue structure that thing looks like without even instantiating it? And so the last two things are spectral estimation and determinant and log determinant estimation in those contexts. So that's sort of the high level that we'll talk about, all right? All right. So this was a line of work we started. I need to click OK on something. I don't want to start randomly clicking OK, given all the trouble we have. Okay, this meeting, it's being recorded. Okay. So so now there's lots of neural networks out there you can download from Hugging Face, whatever. So this work started back when there was a couple dozen, and we did a fine-grained analysis of properties of a wide range of publicly available neural networks. This is not, can I hypothesize this and can I do that? The question is, can you develop theory that actually works on foundational, that works on sort of practical applications people are looking at? So go look at these matrices, right? This is what people actually put out the door. Back then there was order thousands, a couple of years, dozens. A couple of years later there was order hundreds. Now there's order thousands. A couple of years ago, now there's 100,000 or whatever the number is out there. Don't use a two-layer something that's a toy thing. Don't use use people things actually do, and work with good models. And good engineers tend to produce good models. It's far from perfect, but it's not some random thing that you do in an afternoon before a deadline, right? So work with good models and develop theory for good models. Don't develop theory for sort of worst case. That's sort of a guiding principle here. And don't train models, because if I'm training a model and I present you a positive result, you should ask me, where did you cheat? Because you trained the model and probably cheated somewhere to get the result I want, right? So work with publicly available models. So we did this. If you don't believe what I say, you can pip install WeightWatcher. So this is some code that you can do a lot of the stuff we talk about. Long story short, when you talk about 100,000 layers and so on, there's a lot of exceptions that prove the rule. Before the eigenvalue structure of these matrices can look like the following. They can look like the thing on the left. That's Marchenko-Pasteur. If you don't know what Marchenko-Pasteur is, it's the matrix version of just the Gaussian distribution, right? It's what you get for the eigenvalues of random matrices. It's a nice shape like this. It cuts off sharply there. And if you're doing infinite width assumptions in neural tangent kernels, that's basically what you're doing. You may add some complexity, but that's basically what you're doing. It can look like the middle, where it's Marchenko-Pasteur plus a few things that stick out. Statisticians call this bulk plus spike. Or it can look like the thing on the right. The thing on the right is a bad visualization of the wealth of people. Right? The height of people is everyone's 6 feet tall. The wealth of people is a very different distribution. It's much more strongly heavy-tailed. You can model with a power law. You can model with a bunch of other things. But it's heavy-tailed in the sense that you don't have a mean and variance, and you don't see things at 3 sigma or 5 sigma, right? Everyone in the world has someone who's 10x wealthier than them, with one exception, right? And so it's very, very different, and it's hard to visualize something across scales. And so you can imagine a gazillion other types of distributions, but if you take a step back and squint, either things have a scale, they have a scale and stick out, or they don't have a scale. I mean, and they have some heavy-tail structure. So long story short, I don't know if it's on the next slide or not, is sort of everything post. Most of the theories in the left case, maybe bulk plus spike on the right middle, was pre-2013. So state-of-the-art models, 12 or 13 years ago, like the middle, bulk plus spike. So if you take MNIST and you train it to 99%, 0.8% accuracy on a 2-layer MLP, you'll get the middle. All right. Post-2013, everything looks like the right. It's heavy-tailed, it's power law, with a heavy-tailed parameter between 2 and 4, roughly. All right. Lots of exceptions, et cetera, but take that as a leading order bit. So if you're thinking that this stuff looks at all Gaussian, it's not even approximately correct. It's heavy-tailed. The entries are not. The entries have a scale because people work with the entries and normalize this and that. Correlational structure, the eigenvalue structure is heavy-tailed. So you think of this as an ellipsoid that's not aligned with the canonical axes and not aligned with elements, element-wise. So it's sitting off in some funny angle. And the long axes of the ellipsoid are the wealth of people, not the height of people. Right? Very hard to work with because all the tools you have work with the one, but yeah.
So you say that they look more like the heavy weight matrices and modern.
Eigenvalues of weight matrices.
Yes, for a long time, people have observed that as you go deeper and deeper and deeper, the weight matrices and the deepest points tend to be the rank and things like that. Is the field right into them?
Those are all second order bits.
I mean, in the first layer or second layer, are they really that heavy tailed?
Yeah.
Really?
Yeah.
Why?
I'll have me back and I'll spend an hour or two telling you about that. These are strongly correlated systems. These are not IID things. People spend lots of money doing backprop and hardware to cook in correlations. And so, if I want to do a little bit better job, I cook in correlations, I should stretch out that ellipsoid. So I don't do that. The easy way to do that is element-wise or row-wise. So clearly that's, you don't do that. And so there's strongly correlated systems where that's not manifested on the elements. All right. So I wanted to use a theory. Now there's a whole bunch of theorems you can get that have this flavor, but doing exactly this is a bit tricky theoretically for reasons I'll talk to, and this is actually the motivation for the stuff I'll be talking about. But you could use a theory. You can perform model diagnostics. You can make predictions about model quality. You can do post-training modifications for quantization. You can remove layers. You can do all these things. So there's a whole bunch of things you can use. One of the ones that got attention is, I said, make predictions about model quality. This was something we had 3 or 4 years ago. You can take these metrics, roughly smaller power law parameters, good, but it's more involved than that. And I can tell you, I can make predictions about trends in the quality of state-of-the-art neural networks without access to any training data or testing data, just public models. All right, so this is not a theorem. You can easily come up with some perverse thing that violates this. This is like engineering, The ways to build better bridges is to use these design principles. That's what this is, right? So you can make statements about this without access to training data to test data. Okay, so this is how you use the theory. So one of the things we'll talk about random matrix theory is you want this to be a guiding principle. Can we do something non-trivial with respect to this? All right. So the next thing is randomized linear algebra, a very different sort of application. This is the leading slide from a tutorial we gave a few years ago. And on the left is sort of foundations of traditional randomized linear algebra. It boils down to matrix multiplication and least squares in low rank. And at the end of the day, you do some sort of projection. And the projection is a matrix version of just law of large numbers or central limit theorem or Johnson-Lindström or Chernoff-style concentration. So you modularize most of the concentration, the matrix concentration, and then you do a bunch of linear algebra. And the best results are from Banach space theory and this and that. but you can implement these things as preconditioners and you can beat LAPACK. So this is very practical theory in that sense. It uses Johnson-Lindenstrass, and that's a strength and a weakness. Johnson-Lindenstrass gives you guarantees on pairwise distances. It actually uses subspace embeddings, which is a Euclidean space version of that. But you can't. You have to have the aspect ratio to be log n. If you're familiar with Johnson-Lindenstrass as a log n factor, so it doesn't work for large matrices when the aspect ratio is 3 or 5, right? So there's a theory-practice gap. You might just work with Gaussians and try and get stronger results, and then hope that Hadamards and Rademachers and sparse projections have the same results. But that's an empirical question. So on the left, so there's a bunch of questions, and we came at this through the back door with determinantal point processes, and then backed out very sparse notions of embeddings that get much closer to the unbiasedness of Gaussians, but faster in that trade-off space. And there's a range of use cases. For example, on the right, you can use it for optimization, gradient sketching, Hessian sketching. And because you're much better in terms of bias variance structure, you can use it for denoising and a range of statistical things, which you just can't do with Johnson-Lindenstrass because you have no control over that, over the bias in particular. So the interesting point here, if you want good implementations, but also good theory, is not the top left, the TCS, epsilon equals 0.1, where you parameterize it and use something called sketch and solve, get a sketch and solve it. It's not the bottom right, where you use it as a preconditioner and iterate to machine precision. It's sort of the intermediate regime, where I want 10 to the minus 2 or 10 to the minus 4 or 10 to the minus 6. And you might want that just because I want the intermediate regime. You might want that because you're doing quantized computation. That's all you can get unless you do something sort of more complicated. So multi-precision used to mean single, double, quad. You could ask single, half, quarter, and what fraction of numerical analysis goes through to that. And so you can think of quantization as an operator, a little bit like a sigmoid nonlinearity in a machine learning kernel. Right? It changes the operator nonlinearly, but you can ask, can I come up with a deterministic equivalent that gives me the same thing, and then do JL's Johnson-Lindenstrass style results, or maybe something finer? And it turns out the finer things that give you unbiasedness and other stuff has a flavor of a very strong flavor of random matrix theory. If you like technical stuff, Johnson-Lindenstrass embeddings are sort of the lowest level of a hierarchy where you ask sort of linear queries and you get concentration on the forward direction. Less embeddings, and this IID sub-Gaussian, which is a structure of the theory that's sort of under the hood of what I'll be talking about, gives you quadratic form queries, which are much more like, Rayleigh quotients and stuff. And you can do other stuff if you want to do convex functions and Lipschitz stuff. So there's a strong sort of theoretical structure here. And if you want to implement it like in LAPACK, or randomized LAPACK, you can put these randomized algorithms in traditional low rank or QR algorithms, but you could also ask, what class of iterative optimization algorithms could you not do 30 or 40 years ago when LAPACK was developed that you can really do now given the hardware changes and so on? And so we have an effort where we're doing that. So nice theory and nice implementations. And so that's the background as sort of the prior. So I'm not doing financial modeling and looking for noise and there's a market factor and pull out one eigenvalue. That's a fair thing. I'm not doing nuclear structure. We have a bunch of random stuff and a few low-lying eigenstates and look for the difference. So these are traditional applications of random matrix theory. These are the ones that, what I'm talking about will apply to those, but I'll ask slightly different questions because of those motivations. All right, let me pause for a second, make sure people everyone's happy except Rob.
Yeah, sorry, just trying to go back to the WeightWatcher package. Is there something fast and special about that package? I can think of the weight matrix itself. You just say a little bit more about why we should use that.
You don't have to use that. I mean, the matrices are all. Matrices are all 1,000. Yeah, the matrices are all 1,000 by 2,000. So that's not the pain point. The pain point is thinking it through, and there's a lot of subtleties. The structure of the theory we originally developed, the phenomenology, came from statistical physics, and some of the stuff I won't talk about is trying to take those ideas that have to do with volume forms and log determinants and graph sort of ML-style theory onto that. That was the other abstract I sent you, and so it's not a computational pain point particularly, and that package, I don't know if the most up-to-date version may not be public, so you can implement it yourself, but you have to compute heavy tail parameters, a lot of details in getting the lambda mins right, and the way that's done is different than is done in finance and other places where people typically do heavy tail and like EE signal processing, where they do heavy tailed. Yeah. So just a lot of little details, and that's a snapshot. I mean, there's a range of other things you can do, but so and still work in progress. The best way to choose that minimum eigenvalue estimator and stuff. So you could do it yourself, but it's just one of these things. There's a lot of ways to do it wrong. Yeah. I mean, this is a particular way, but it's also hard to work with because it's a chainsaw, and we don't have We haven't simplified it. I mean, the whole talking about random matrix theory for modern machine learning is to take these ideas that are obvious if you're, I'd say knee deep, but neck deep in random matrix theory and statistical mechanics learning, and basically try and come up with a structured theory that is much more usable. And we're sort of halfway there. All right. So random matrix theory, linear to nonlinear, shallow to deep, asymptotic to non-asymptotic, et cetera. Okay. This is okay. So we do big stuff sometimes, but this is big in a much more modest sense. You do a deep neural network of 2 layers, right? We used to do with the randomized 3 is deep. We used to do 1 layer deep with a identity nonlinearity. So we did a lot of the randomized linear algebra. That was the joke. So I think these things are sort of toys, but I just kept this figure in just to say, see, there's some circles there, So the first layer is a matrix. It's a linear transformation, and after that, you do stuff. You may have an activation. You may have other things, which is in some sense fundamentally nonlinear, and so it's not clear that linear stuff has anything more than 0 to say about that. And so that's what we want to get into and try and understand the granularity of this a little bit. So it's sort of a high level, and then I'll get into a few specific. So the general goal is you want to analyze and optimize some large scale model. It's a matrix X. It may depend on parameters. So, you do the usual iteration and it's not convex, but then I feed it through some M that, you could parameterize in different ways and put the nonlinearities in that, or, in a subset of that, instead of have 2 composed things. And then I want to feed it to some loss function, an entropy or an MSE or something else. So this is the form of the thing you want to do. So it's not just pull out a matrix and get some eigenvalues. The objective is the evaluation of that M via some performance matrix F, the MSE or the log determinant, all right? All right, so a couple technical challenges. One is that these things are high dimensional in some sense, but what does that mean? A lot of rows, a lot of columns, neural scaling laws both diverge together, so you might not concentrate. And so the thing you're dealing with, you may not concentrate. That matrix, first of all, has this nonlinear filtering, so that's a problem. And even so, it may not concentrate. And so you typically will want to compute some low dimensional loss function, which is a number. And so it could be a quadratic form of it or something. And so concentration of that function F. So that's key idea 1. I'm going to concentrate not the thing. I mean, if you can concentrate the thing, that's good, but it's overkill. Jail's overkill, asymptotic stuff is overkill here. We want to concentrate some function of the thing. Analysis of eigenfunctionals. So a lot of this stuff goes through what's called the Stieltjes transform. And the Stieltjes transform is a matrix. I look at the inverse, I regularize it with this complex function thing, and then I take a dot product. I take a trace of that. And that gives me eigenvalues. I could take other things. I could take a quadratic form of that. So traces are one type of quadratic. I could take a quadratic form of that. Right? Turns out that quadratic form gives you eigenvectors. In machine learning, oftentimes you don't care about the eigenvalue. You want the eigenvector because you swoop along it. And you can ask if the first 2 eigenvectors, the eigenvalues are very close, they could rotate 90 degrees, and so that's a layer of texture on top of it. But I want to get not a number that's the eigenvalue distribution or the set of eigenvalues in range. I don't care about that. I know that I don't have an eigenvalue separation, so I don't want to find a separation and then ask about the eigenvectors. I just want to get the eigenvectors directly. Otherwise, I'm being wasteful. So can I come up with a deterministic equivalent for the resolvent? So one example of that is take the trace and get a Stieltjes transform and get eigenvalues and do the usual thing. But I could do other things. I could come up with other scalar functionals that are not the Stieltjes transform, but that work with this inverse. And the key idea, Johnson-Lundstratz gets these forward results on pairwise distances, but it doesn't get inverse results. It's much less robust on that. And so the random matrix theory gets that, essentially, but not in a worst case way like the machine learning and theory of algorithms people do. So we want to get a deterministic equivalent for this basic resolvent and then work with that directly. So sort of one step prior to the usual analysis. And then there's nonlinearity in the machine learning model. If I take my matrix and I filter through a quantization operator, or I filter through a sigmoid nonlinearity, and I'm way out here on the sigmoid parameter or something, there's not so much you can do, right? Go home. But you can imagine that in the intermediate regime, you may not have changed it totally, or and so you might hope that in the same way as there's a Taylor expansion for low-dimensional functions, and you say they're approximately continuous, you could do something analogous for these high-dimensional objects, or for scalar function versions of these high-dimensional objects. And that's basically what we'll be doing. You can use tap expansions. That's a statistical mechanics style theory. And high temperature perturbations, basically. This is sort of not that, but it's a little bit related. So think of it as, what would it mean to come up with a linearization of something in n dimensions, right? The usual functional analysis approach is to take one dimension and then take the cross product of 2 and 3 and n's, and now you have a hypercube with 2 to the n corners. So it can't be that. It's got to be something else. And so this will be that something else. All right. The next couple slides will have lots of words. Just ignore the words if you want. A high dimensional equivalent is basically I have a random matrix model. I want to come up with another high dimensional thing. Think of it as deterministic. It doesn't need to be that is different than that matrix. And so the matrix does not converge in a law of large number sense or central limit theorem sense. But I have this thing that's easier to work with, and that if I query it with linear queries or dot product queries or some other class of scalar function queries, I get the same answer as if I query this high dimensional equivalent. So it's equivalent in that sense. So, if f of m phi minus f of m phi tittle goes to 0, so there's a limit, there's a concentration. This is, you can come up with non-asymptotic versions of this. And so I'm going to say that the two are the same with that left-right arrow in the definition. All right, so the details, don't worry about, but that's the sort of the basic idea. I want a high dimensional equivalent. A key thing here is the notion of high, there's a minimal set of things that you can really understand in high dimensions, right? And you just don't have functions that are like these functions in calculus where they wiggle around like this in 2 dimensions, right? Because the only things that are sort of statistically meaningful might be distances and angles and things like that, right? And then what you need to know about distances and angles is that depending on how you mean center, you just get one of a few things, right? If you have something that's not mean centered, there's a character, if you scale it right, there's a characteristic distance where the mass is, right? It's distance 1 or whatever. If you mean centered, it's distance 0, but you get some 1 over root n variance from some central limit theorem. So if I want distances between 2 points, they might not concentrate at the origin. I have 2 points from the same distribution. They might not concentrate to each other, but certain functions of them do. And then the reason they don't concentrate to each other is because they're 89 degrees apart. They can't concentrate to each other. Just think about that, right? And so if I want the distance between 2 points, that doesn't concentrate either. So there's certain types of concentration you can have around, say, a mean. And so you have to ask slightly different questions. And one way to, and this is basically why the high dimensional objects, unless you go to very conservative scaling regimes, don't concentrate. They just can't. And you can just see that with a simple vector of a few elements. All right. High dimensional concentration of scalar observations. I guess I've sort of alluded to this before. Let me jump over that. Lots of words here. But what you need to know is that roughly think of 2 regimes. Right? One is a law of large numbers regime, where basically things concentrate in a very strong sense. So I scale the right way, and I get a number plus or minus a variance that's very, very small and goes to 0. Depending on how I do the mean centering and the stuff on the previous slide, I can take that number and set it to 0 and get a CLT, a central limit type theorem regime, and get CLT type concentration. And I mentioned these because this isn't just a matter of choosing 1 over n's or 1 over root n's, that seems sort of people choose it for convenience or whatever. These sort of really will mean something different in terms of the types of expansions and linearizations you can get if you quantize or something. So I'll give you an example of that. All right. So how would you do linearization in the 2 scaling regimes? So the usual Taylor function expansion, I'm working with a deterministic function from R to R, and I do a Taylor expansion, right? You might imagine that if the function is from some insane random space or some high dimensional space, but that if I work with a scalar functional of it where the variance is extremely small, formally, I might be able to do the same Taylor expansion. And then you might be able to justify that with some complex sort of measure theory. It turns out that's the case. So you can do a Taylor expansion. And so literally I have a scalar function, I measure it, and I just do a Taylor expansion around that. And so it's not a deterministic function, it's a random function, but things concentrate so nicely that just works. And you can think of it in terms of functional analysis, which is sort of what measure theory is built on. So if you concentrate extremely strongly, you just use your usual intuition. If converters do Taylor expansions. If you concentrate less strongly, think of the variance of the Gaussian with the quadratic. If that variance is the same level, so I'm trying to estimate the leading order term of the Taylor expansion. If the variance for that is the same as the next order term in the Taylor expansion, I can't ignore the higher order terms. So do I go home or what do I do? So I can go back to functional analysis, and you can use Hermite polynomial expansions. Hermite applies if there's a Gaussian distribution. There's other types of orthogonal polynomials that apply if the tails behave in other ways. So I can do a Hermite polynomial expansion. And so if you don't know what that is, ignore it, just realizes it is a more complicated way to do a high dimensional expansion. But if you do know what that is, it's the same playbook as we had before, right? You could do this with deterministic functions. That's what they do in functional analysis. You can do this with random functions. So there's a measure theory thing going on, and I want to get a Hermite polynomial expansion. So these are two different ways to linearize depending on the regime you're in, and depending on whether I do LLN or CLT scaling, I should do one or the other. Right? So clearly, the intuition is easier if you do the LLN stuff, and that's clearly not as realistic as the CLT stuff. So you do some of the intuitions from LLMs, but realize it doesn't go through in a lot of cases. All right. So that's sort of the high level bit. So there's a lot of moving parts here. I just want to illustrate sort of in the simplest possible setting, which is covariance matrices, a couple of the moving parts, and then we'll say how to use this. Okay. I think so you're either classical, and by classical I mean not proportional. So by proportional I mean you have a matrix and you have two parameters, this M and N, or M and P, or M and D, and I let those two parameters diverge together. Right? It's not that I fix one and let the other diverge. If I fix one and let the other diverge, I get LLN or CLT. But if they both vary together, and you might say this sounds, like it's going to be more complicated, and it is. But this is a regime that's sort of realistic, right? If you do neural scaling, you scale model and data and compute. You're varying two things together. If you do a range, I mean, if you're heavy-tailed, this is why we get the heavy-tailed structure. So the classical is a bit overkill. You get an extra log factor or an extra polynomial factor, and things concentrate much more strongly. So it'd be classical or proportional, and I can be asymptotic or not. And I'm not going to, and I'll deal with the linear versus not linear in a second. So law of large numbers, LLN, your asymptotic statement, and you're in the classical regime. You can use sample covariance concentration if you're a non-asymptotic version. So this is like a matrix version of the Chernoff inequalities, right? There's matrix Chernoff inequalities, and so this is the first cousin of that. And so it's a non-asymptotic statement that holds for fixed N and P. But you're in the classical regime. In order to get that to concentrate, you need to not have N and P diverging together. Classical random matrix theory is on the top right, Marchenko, Prishchurla. They do things asymptotically, but they work in the proportional regime. The aspect ratio is 2 or 3. And so if you see phase transition plots, they typically say a phase transition happens here and not there. It's because they can get precise enough to be in the asymptotic regime and see exactly where the exact asymptotics is. And so essentially what the next couple slides will flesh out is not the Marchenko-Prishchurla, which is about eigenvalues, but an asymptotic or deterministic equivalent for resolvents. So one step back on the resolvents, and then a non-asymptotic version of that. All right, so that's the high level bit. I'll zoom through them on the next slides with lots of words, but that's the high level thing. So I can be asymptotic or not. I can be proportional or not. It works on matrices, and then because of what I talked about before, I can do expansions. Exactly how I do the nonlinear expansion depends on what regime I'm in, and I can deal with things like sigmoid nonlinearities and quantization. All right. So hopefully you recognize this. This just says you get a sample covariance matrix, you mean center and whatever, and normalize and put it in standard form, and it converges to the identity. All right. So one of these things, it's parameterized to hold in the classical regime, right? So it's not immediately obvious how this would apply, right? It smells like CLT, but it's a little bit different. But it's the form of the parameterization, the same way as the form of the parameterization of Johnson-Lindenstrass that came from theory of algorithms only works, in that regime where it's fine to be biased. I'm not unbiased, but I get a error on the forward error pairwise distances. Here's a non-asymptotic in the classical regime. Ignore lots of words. Just look at the equation. C minus the identity is less than some constant C1 times some factors, right? And if you've seen these sort of Chernoff and matrix Chernoff bounds, you can prove that something like this holds, right? It's not a right arrow that goes to 0 actually exactly, but it's less than something that depends on some constant, and the max of some factors that depend on the variance and the parameters, right? So this is sort of classical stuff in some sense. All right. This is a proportional regime, and this is eigenvalues. Okay, so there's again a lot of words. Let's look at the equation. This equation looks pretty different than the others, but it's pretty similar. And so what you want to say is that mu, the eigenvalue distribution, before I just said the difference in the covariance matrix and the identity, and so that's a spectral norm, and so that's really a statement about eigenvalues. So all the eigenvalues of that covariance matrix are 1, namely what they are in the identity, plus or minus delta or root delta or whatever that. So they're all close to 1. This mu is 1. It could be if all the eigenvalues are on 1, this would a delta function spike at 1, but they're not. They're spread out a little bit. And how are they spread out? They get spread out by exactly that functional form. So this Wigner semicircle law is a semicircle. This is a slightly more complicated expression, but think of it that way, right? It's just some function and it's spread out around 1. And so this is the exact distribution you get in the asymptotic regime if you're interested in eigenvalues. And here's some functional forms, right? So depending on the aspect ratio and things, you get this spike that looks pretty close to 1, but it can also be spread out. Mass can be at 0. So you get it could be a lot of different things. Depends on the aspect ratio. I like this plot because even on the on the top right, when the aspect ratio is 10, you have eigenvalues that are 1.5 and 0.5, right? You're nowhere near 1 plus or minus something small. When the aspect ratio is 1,000, you're still 0.95 to 1.05. So unless you're writing academic papers, you never see matrices this rectangular, right? So this regime really is the one that sort of you need to be worrying about. Here's an asymptotic deterministic equivalent for the resolvent. This is something that think of it as as the asymptotic version of the Marchenko-Pasteur law, but it's on the resolvent, right? Not on the Stieltjes transform, the trace of the resolvent. And so there's an equation there. If you solve that equation, you get a distribution like we had before. So this is just to say you have a statement, a theorem that says I can work not with the Stieltjes transform, but the resolvent one step back and get an analogous result in the asymptotic regime. That's easier. Really what we want here to speak to machine learning people is a non-asymptotic statement. And non-asymptotic random matrix theory is just much less mature. So I like this result because it's one of the first that sort of makes that explicit. You can imagine lots of extensions of this, which is actually worth following up on. And so this is the expectation of Q as the resolvent is less than constant over epsilon times 1 over root n. And Q is M, that function times the identity. And so it's something concentrated near the identity or something that's spread out a little bit around the identity. All right. So all this is to say, we can go back to random matrix theory and tear apart the Stieltjes transform, get under the hood, work with the resolvent, and get asymptotic and non-asymptotic versions of a bunch of those basic results. And so we have a longer thing being written up. This is in a paper that's going to appear in a review at IEEE, something or other, proceedings of the IEEE, I think. And so high dimensional equivalent, you can come up with a linear and deterministic, 2 different variants of it. You can work with a linear model, nonlinear shallow or nonlinear deep, and you can ask a bunch of questions. And so the types of questions you can ask, and this is just a proof of principle, is a hello world set of results, is I want to understand the scaling law of the training error. All right, so this is on a linear random matrix theory, but I fed it through a sigmoid nonlinearity, so it's not infinitely wide. It's got to come up with a deterministic equivalent, and then this thing has, for simplicity, that review has the asymptotic results, but you can have non-asymptotic versions of that. And so I want to understand the scaling law of the training error. And if I interpolate versus not, I get 2 very different scalings. This is a baby version of neural scaling laws. I want to do double descent. I see spikes in covariance structures and volume forms that govern generalization. And I can get that. And whether I'm in a linear model or a nonlinear shallow with sigmoid nonlinearity, et cetera, you get slightly different results. So that's remark 7 and 10. I'm not going to have those remarks in the slide deck, but it's in the write-up. And I can ask questions about running dynamics. I think a lot of NL people like running dynamics, but it's a much harder set of questions to ask because it's a dynamic thing and not a static. All right. So this is just a plot to say you can, all these nice things like spikes and so on you can get. All right. All right. So let me pause for a second because I want to shift to some other things. So there's a lot of stuff there. If you've been doing this sort of stuff for years, you probably got a different set of things out of it than if you're a student here doing on it just sort of for the first time, but hopefully you got the high level bit. And the high level bit is that there's a lot of stuff from random matrix theory that's been traditionally parameterized in the proportional regime for linear models asymptotically, and you can apply them to nonlinear models. This is in the worst case, things can go insane, but for a really wide range of nonlinearities that people use in machine learning. And you can apply them in non-asymptotic form, and you can apply them on things on the resolvent 1 step before the Stieltjes transform to other scalar functionals that will give you eigenvector information that can do classification or whatever. So a range of different things like this. So many questions. I'm sure everyone's fine except Rob. Do you have a question to clarify? Yeah. All right. One example I like that sort of no pun intended, concentrated my understanding of this is we oftentimes will parameterize things to say, well, I choose two Gaussians and I choose the scaling such that their means are pretty far apart compared to the variances. Now, when the means are far apart compared to the variances, there's nothing to do, right? You just look at nearest neighbors and then classify networks, right? And so that's used as a theorem to justify an empirical evaluation. When the empirical evaluation doesn't have the aspect ratio of 1,000, it has the aspect ratio of 3. And when the aspect ratio is 3, that means that the scaling, the means are not this far apart. So you can easily come up with situations where you have a scaling where the means, I have two clusters, A and B, I want to classify them. The intra-distance on A looks like this. The intra-distance distribution on B looks like this, exactly the same. And the interdistribution between points in A and B looks like this, exactly the same. So the pairwise distributions are exactly the same. Feed it into vanilla, kernel spectral clustering, never mind 57-layer neural networks, and boom, you can get a class separation. So that tells you that this pairwise information from Johnson-Lindenstrass, when you're more conservative on the problem parameterization, really is not saying anything but why the method works. But it turns out you can use exactly the style of analysis and say that's why the method works, right? Spectral methods include pairwise and triples and quadruples of information in certain subtle ways. You can think of it as like an iteration in a heap kernel. And so it can go beyond just that pairwise information to get both forward and backward information. And so you can get perfect class separation, even when all the pairwise distances are the same. So if you're using an analytic technique that requires, implicitly like subspace embeddings or Johnson-Lindenstrass does, it can't be describing what you're doing. And I think there's a million variants of that, but just the simplest possible case, get an eigenvector, do a sweep. And you see that here. All right. So applications. So we started at 30 after. Okay. So heavy-tailed mechanistic universality was a coin that Charles and I, it was a term Charles and Martin and I coined when we were doing the WeightWatcher stuff. He was sort of a lead with me on a bunch of those things. And the idea is to tap into the idea of universality, but in some heavy-tailed sense, because you see something like this in a lot of systems. And the universality is much weaker than Gaussian universality. They want to say more than 0. And as a very practical matter, I want to come up with a random matrix model that has heavy tails on its eigenvalues, but not its entries. Because it's very easy to get heavy tails on eigenvalues if you put heavy tails on entries, and that trivializes that, because that's not what you see in real neural network models. So I'll describe that, and then maybe just very, very quickly, I'll mention, we can compute on large things using this idea, connections with free decompression and free probability theory. All right, so the connection with heavy-tailed mechanistic universality is, this was not obvious when we started this about 2018 or whenever this was. Now people realize there's sort of heavy tails everywhere, right? You see it on gradient norms. And now people see that because they like to parameterize problems in the gradient norms, and so it comes out there. You see it on eigenvalues of Gram matrices of neural networks. You see that on a bunch of places. You see that in the weight analysis we did. And you see that in neural scaling laws. I mean, neural scaling laws say scale, model, and data and compute, so none of them saturate. If one of them saturates, you're in some regime, and the model is much more brittle than if you don't force it to saturate. You get things like hallucinations with LLMs that people complain about, right? But that's on the flip side of getting strong neural scaling, heavy-tailed mechanistic universality. So new RMT for heavy-tailed mechanistic universality. So the question is, can we come up with something maybe that gets nice properties on the eigenvectors, right? Because that's going to be hard to, but the eigenvalues can be more flexible. And I don't want Gaussian concentration, right? That's a bad thing. I want heavy tail concentration, whatever I can say there. So how would you do that? So that's basically what we want to do here. All right. If you don't know about neural scaling, this is a neat idea. The ideas are from sort of statistical mechanics with scaling laws. And what you see is that if you increase the amount of data and compute in a lot of language and other neural network models, it's not that the models keep getting better, which they do. It's that they keep getting better and don't saturate. You can keep getting better and have diminishing returns. They keep getting better and don't saturate. So on a log plot, it keeps going down. And so if you see this over scale 1, scale 2, scale 3, scale 4, and you're at OpenAI in 2018, whenever it was, you bet the farm that this trend will continue one more order of magnitude, and they did, and they won. So, so think of this as a phenomenology for these things. This is something we use to predict trends in the quality of generalization, the quality of models without looking at without looking at the training data or or any training protocols, hyperparameters or anything. And just to mention, you can ask, how does metrics for model quality correspond with generalization metrics that people in ML like to prove theorems about? And the blue and red going in opposite directions basically mean here that they anti-correlate. So you turn a knob one way, you get better generalization error. In theorems, you got to turn the knob the other way to get better model quality. And by model quality, I mean good engineers put out good models online and have a table of numbers, and their model's the best. And 6 months later, a different engineer puts out a model, table of numbers, compared to the previous one, my number's the best. You know, and so by model quality, it's self-reported quality. The exact metric is different in different domains. So what might constitute universality in these sort of weights? So in random matrix theory, universality, in some sense, denotes the emergence of this sort of system-independent properties, right? It doesn't matter if the entries are Gaussian or any other distribution with mean 0 and variance 1 or whatever. I get eigenvectors and eigenvalues that behave the same way. In statistical mechanics, it typically arises in systems with strong correlations, right? And so you can think about one way to prove Gaussian concentration is to do a renormalization group style analysis. That when I get 2x more data, things concentrate on the first and second moment, and then the other ones die off. You could ask about doing that more generally. And so it arises, and the more generally would actually work for systems that are not independent, but have these strong correlations. And it's characterized by observables, experimentally measurable observables that don't depend on the data or training protocol, but depend on the final product. Heavy tails in the eigenvalues, neural scaling laws, these sort of very coarse properties. Weight matrices are not random. Nevertheless, these RMT tools that I've been talking about so far are useful descriptive framework. So I talked about the weights. In use of time, I won't go into it, but similar things hold on Jacobians and other things. I think this is interesting because Jacobians are easy for people to parameterize a lot of theory around. The weights are a little bit strange in terms of ML framing. It's good for phenomenological theory, but not theorem-style theory that ML people prove. What I'll talk about here will apply to both. So you see similar sort of heavy tails on NTK and other spectra. Okay, so heavy tail distributions informally, rather than decaying exponentially, e to the minus x, the distributions decay as x to the minus parameter alpha. So x to the minus 2 or x to the minus 3, I think, right? So possible ways to get this. You could have heavy-tailed elements. Theorem heavy tail on the elements, you have heavy tail on the eigenvalues. I said we don't want that, but you could do that. There's some results on that. You could have a Keston-style mechanism, which basically says if I iterate and something is norm 1 after the iteration and I iterate, it stays norm 1, right? 1 to the 50th power is 1. If I get something norm 1 plus or minus something very small, certainly the CLT regime, but even the LLM regime, if you squeeze hard enough, that variance will blow up over time. And so you get heavy tails. Keston has a general mechanism to do that. You can also just sort of say the population's heavy-tailed, so power in, power out. So we don't want that either. Keston worked, but we didn't want a dynamic. So we're actually going to look inside the model and do something exogenously. So we had an approach where we dealt with various types of structured matrices. And sort of essentially what we're doing is to say, I want a model of a certain form that's rotationally invariant, and I'm going to go in and fiddle with the eigenvalues. And random matrix theory, most of the results have to do with these global eigenvalue properties, these plots I was showing before. It can also give you properties of local eigenvalues. Have two eigenvalues next to each other behave. And eigenvalues are eigenvalues. They're not IID things. So in particular, they tend to repel each other. The statistics of them are not as if they're IID, it's as if they tend to repel each other. So it's much more uniform inside that bulk than it would be otherwise. And so we're going to go in with that and fiddle with it, basically, in this model. Okay, so modeling framework. We want a modeling setup that says, I want to minimize something. This is F plus lambda G, right? This is machine learning, empirical risk minimization. But there's expectations in Kubrick-Lieber, and it's a little bit more complicated than that. But think of this as I want to do that. But I really want to set up where I'm going to have two parameters, right? So it's not just a single regularization parameter. I'm going to want essentially a second temperature parameter. And it's because essentially I'm going to have a hard constraint. I want to control two things. So it's a little bit like an augmented Lagrangian approach to optimization. But I'm going to have a second parameter. I'm going to anneal them at two different rates. All right. So P is a set of probability densities. And I have a temperature parameter, and I want to model this. So there's a lot of things that sort of boil down to this. And if you do pack bays and things that ML theory that they like, it'll boil down to something like this. And I want a feature learning setup. So think about explore, exploit, or there's different regimes. There's the whatever you call it, the early regime, and then there's the feature learning regime, and whatever they call the latter regime. So they're going to have two raised temperatures, one to control the coefficients and one to control learning rates. All right, and so if you take something of this form, then proposition, you're going to get an optimal feature density of some form. So there's nothing particularly complicated here. I mean, so let's not, you don't need to go about the details, but this is something that theory people would like. All right, so based on that and the other evidence we saw, we can sort of have a, let's say for trained feature matrices, I'm going to have an ansatz that it's going to look something like this form. So it's a determinant of m to the minus alpha exponential beta trace of this thing, and then a probability distribution. So parse this. If you do just you approximate matrices as IID Gaussians, that exponential is going to be it's going to be whatever n transpose sigma m. You know, it's x transpose ax. It's a quadratic form. You can remove that matrix, put it in front. It's a volume form, and you're going to get determinant or log determinant, and these are Gaussian integrals, so it falls out. So that's that exponential, and that determinant of m is what you get, but you notice that beta is not alpha, and they're not related. So there's going to be two parameters now. These are like the two temperature parameters, and we'll be able to play with that. All right, and this follows inverse Wishart type sort of densities. All right. So I told you that we went in and wanted to fiddle with the eigenvalue spacing. So those alpha and betas correspond to this kappa here. So I want my distribution to depend on some v, which is a normalization, times an eigenvalue difference. I said there's a characteristic difference. If that alpha is, I think if it's 1 or whatever, 2, I get the usual thing. But if I can change that ratio by fiddling with the alpha and the beta, which corresponds to the learning rates and other things in that dynamics. And I can adjust that. It corresponds to the structure and the structured matrices that I sort of alluded to if you want a static version of it. Right? And it's using beta ensemble that Dimitri and Edelman had, way back when. And that's a classical random matrix theory result, feeding it into that ansatz, which is going to be the HTMP. All right, theorem. I do this. I get that first bullet, MP sub gamma. That's the Marchenko-Pasteur stuff we've been talking about, where gamma is basically how wide that distribution is, the aspect ratio. So if kappa is large, goes to infinity, I get Marchenko-Pasteur, and I get HTMP, high temperature Marchenko-Pasteur, if kappa goes to 3, 17. All right, so I have a modeling framework where I can get, depending on that eigenvalue separation, I can get the classical universality results, or I can get these results. We don't have universality results for this broader class, but that's the conjecture that we could. And this free probability, that's what that free convolution thing is about. And I can separate things between bounded and heavy-tailed. I can get inverse gamma near 0. I can get power laws on the top. So the weight is power laws on the top, and I mentioned you might want to regularize the bottom. Other things are power law on the top and bottom. So this is sort of consistent with a bunch of this. So we have a random matrix model. It's that ansatz. There's a way to fiddle with the structure of that operator to get Marchenko-Pasteur and a broad generalization of things, but in particular, Marchenko-Pasteur, which is localized Gaussian universality class, becomes very delocalized and get all sorts of stuff in between. Power laws for the limiting density contain, this is sort of stuff I described. So this is the first model that will do something like that, I think. Everything else is power law and power law out, or somewhat on the elements. Okay, so application 1. These are 3 applications. As you know, in the business, you got to get a paper in, so you need an application to point it to. These are sort of toy applications. I wouldn't take these to a desert island. I'd take the setup I've been talking about so far to a desert island to sort of beat the proverbial tiger. These I wouldn't take to the desert island. These are sort of proof of principle. But neural scaling laws. A very simple setup, least squares, et cetera, et cetera. If I do that, it's a relatively straightforward application to say, plug it into that model, plug it into that functional form, you get a generalization that behaves this way. And this is a variant of what I talked about before in that slide when I said you can get neural scaling and some other things, right? And so you get, not e to the minus n, you get n to the minus some set of parameters. Can you do this more generally? Can you do this with nonlinearities? Can you do this with 3 layers? Can you do this? I'm sure the answer to that's yes, and we couldn't do it over the last weekend, so I don't know but these are obvious open questions raised by that. If you're looking for the good problems, optimizer trajectories. I want to get it not on the weights, not on the Jacobians. I want to get it on gradient norms. So now I can run this, and I can get the del tittle ln norm is the norm of stochastic gradients during an SGD training process. And x goes to 0, x goes to infinity. So I have a distribution of gradients. They're not all one size. They're heavy-tailed. That's been observed previously. And I can get this with this scaling on the top and bottom end. So you can assume the gradient dynamics are Gaussian if you want, which is not even close to true. You can work with something closer to this and try and get results. So I think there's a bunch of open questions here. And the 5+1 phase of training. I told you there was three. There was Gaussian, there's bulk plus spike, there's heavy-tailed. You can also be between these two and be between these two. There's some subtlety in how you go between the two. And then there's +1 versus a degenerate state. So the top left and the top right and the bottom middle are sort of what I showed you before. But you can get, those three as well as the things that interpolate between the two, and you can get collapse on and lose degeneracy, get rank degeneracy. So you can reproduce a bunch of these things. All right. So the master model provides, I think, a general RMT framework, backward compatible with RMT. This particular stuff is asymptotic, but yeah, I'm sure we can get non-asymptotic versions of that. The HTMP, the high temperature Marchenko picture, has this extra temperature parameter that allows us to become heavy-tailed, and essentially we go in and control the eigenvalue spacing. You can say that's a cheat because, but it's a legitimate random matrix model to understand these things. If it's a cheat, it's a cheat in the right direction. It's much more realistic than previous stuff. We assume IID elements or something. And there's a data contribution. There's an eigenvalue structure, there's a training dynamics, and it provides a nice framework to tease all these apart in a way that makes sense to random matrix people, I think, and machine learning people. All right, with that, let me wrap up. I'm out of time. You can do spectral estimation with 3D compression. And so if you're interested in getting matrices that are so large you can't even do matrix vector multiplies, say the matrix I have is an instantiation in the sense of free probability theory of a much larger one. There they have an idea that you can compress matrices. We ran that in reverse through decompression. And you get a differential equation. You got to do some sort of numerical analytic continuation on a complex plane, which sort of made me happy because I was afraid of that until we did it here. It's a hard numerical problem. We're solving linear algebra by solving PDEs. Usually people do it the other way around. And you see, I can measure the thing in the middle there where it's very close to 1, and I can say the thing that's 10,000 times larger is spread out in this particular way. And you can do that on real data and so on. So there's an very open code. We can do similar things with log determinants. There's the NTK on ImageNet, and you can get under scaling assumptions and so on, and it will scale. So grab me afterwards if you're interested in some of those details. All right, so some motivations from machine learning and neural networks. Heavy tails and eigenvalues are everywhere. Classical random matrix theory basically has nothing to say about that. So motivations from randomized linear algebra. Right, I want to do various matrix computations, but I want stronger control than Johnson, Lindenstrass, and asymptotic analysis with Gaussian gives. So based on that, you can use basically the idea of non-asymptotic deterministic equivalence, which is just a heavier duty technique than LLMs and CLTs. I can have asymptotic versions of that. I can have non-asymptotic versions of that. Big open questions on the non-asymptotic random matrix theory and I can feed that into relatively tame nonlinearities in the sense that a sigmoid with parameters not way out there, quantization not extraordinarily aggressive but moderately aggressive, and then I can feed that into getting random matrix models with heavy tails and the eigenvalues. I can get log debts under neural scaling assumptions. I can use these PDEs to do this extrapolation of the eigenvalues probably more generally. So I think there's a lot of good directions if you want to apply RMT to machine learning. But also, I think machine learning sort of opening the doors, even if you care nothing about that, but just want to say this is what people care about, and I want to do RMT still. There's a whole bunch of this core random matrix questions, and as you probably know, these are one step removed from asymptotic statistics and pack Bayes and all this sort of stuff. So a lot of good stuff here. So hopefully it teased some of you and you'll want to follow up on some of these things. So that sounds good. So thanks for your attention.
In the interest of time, if anyone has questions, please feel free to stick around. Otherwise, thanks for joining us.
All right. Like that?
I don't think Rob did, but I love.
Well, Rob, he's what can you do with him?
Really